Now let's talk a little bit about one-sided limits. We kind of talked about this in our last video because I kind of threw some in there and then I was like, hey, surprise, this is what it means when you got a little minus sign. And so that's really what the one-sided limit is all about. We know that a limit doesn't exist unless the limits agree from both sides. But if they're asking specifically for a one-sided limit, we're just saying, does the limit exist as we come from the right or the positive side, or does it exist as we come from the left or the negative side? So again, those are one-sided limits. So if both sides of those limits agree with one another, then the limit exists at that point, but perhaps only a one-sided limit exists. So again, it's possible that we're only looking at a one-sided limit, and those obviously exist more often than just a general limit. If I were looking at the function, the square root of 4 minus x squared, as we can see, the graph of that function is a circle. If I were asked, or a semicircle, excuse me, if I were asked to find the limit at x equals -2, I could not, because from the right, obviously I do have a function, but from the left, there's nothing over here. So I can look instead at a closed interval, closed because it includes that point -2. So if I were asked to find the limit at x equals -2, I couldn't, but x equals -2 from the right-hand side, I could follow this down to -2 and see that that y value would be 0 at that point, and so the one-sided limit would be 0. So again, we've talked about continuity on an open interval. This is specific to a closed interval, and again, closed interval just means that I'm dealing with those closed brackets on each end. And if it's continuous on the open interval, AB, whatever those end points are, then it's continuous on the closed interval, assuming that the left-hand side, the way that the function is defined at that point is equal to the limit at that point, and same thing for the right-hand side. Whatever that function is defined at that point is equal to the limit as we approach that point from the left-hand side. So again, the right-hand side for the left-hand bound and the left-hand limit for the right-hand bound. Again, don't get confused with all of that. We're basically saying, does this point equal the limit as we approach it? Does this point equal the limit as we approach it? So now let's talk about the continuity of the function radical 1 minus x squared. First of all, it's important to understand what the domain is. Why is the domain -1 to +1? Well, because we know that the radicand, which is 1 minus x squared, must be greater than or equal to 0, because we don't want to take the square root of a negative, or we'll end up with an imaginary number, which is no fun. So just do the algebra. We get x squared is greater than or equal to negative x squared is greater than or equal to -1, so positive x squared is less than or equal to +1. We know that if we were just looking at x squared equal 1, my answer would be plus or minus 1, so I could find my intervals of -1 and 1 and then do some checks, and I would find that this is the section that I want, which of course is from -1 to 1, and including both of those values because of the or equal to, because it's okay to have a 0 inside the radical because the square root of 0 is 0. So again, now we're going to look at the continuity on the open interval. So we're just going to use the open interval, make sure that that function is continuous over that interval, and then we're going to look at the right-hand limit and left-hand limit of the left-hand bound and the right-hand bound. And we can in fact confirm that because the limit as x approaches -1 coming from the right is 0, and that's the same as f of -1, because if I plugged -1 up here, I would get 0. And if I plugged it in from the left-hand side, again, direct substitution, I get 0. F of 1 is also 0 because the function is continuous on the open interval and the left-hand and right-hand limits match the value of the functions at those points, we can confirm that it's continuous on the closed interval.